All right, so welcome to the last week of Cal 2, right? And we have our final, next Thursday? Thursday at 12:30. We'll talk about the exam on Thursday. We are going to try and finish up 8.6 and 8.7 in the next 2 days. We won't see Chapter 9. I still have to figure out, I'm offering a bonus lecture. I've been kind of throwing in the air whether or not I'm going to do Chapter 9 stuff or if I'm going to do the Fourier series like I had initially intended on doing. So I don't know yet. Yes?
How many points is it?
I don't know. I'm thinking like 5 points on the final. 5 points on the final exam. But I need to still determine the time. So let's finalize that on Thursday. All right? How many of you would want to do it like this Friday? Mm-hmm. Think about it. This Friday versus next week sometime. Think about it. All right. So 8.6, if you were here a little while ago, I usually write the word focus on the board every time, right? But I wrote intense, like today is going to be pretty intense, all right? So please follow along, ask questions if you have them, but you're probably going to feel a little bit like, what's going on here? Maybe, I don't know, we'll see. So this section is called Representing Functions as Power Series. Last section, what we did is we looked at what a power series was, and we figured out how to determine the radius of convergence and interval of convergence of a power series. And what did we use to do that most of the time? The ratio test, right? We're going to kind of step away from that now, and we're going to see how we can represent functions with power series. So we take a function that we're familiar with, but instead of writing what we're familiar with, we represent it as a power series instead. And so the question becomes, why would you ever want to do that? Right? Why would you ever want to represent a function that you're happy with a power series? So take a look at this integral here. This right here we would call the integrand, right? That's the thing you're trying to integrate. And we could consider that to be some function of x, right? If I asked you to integrate this right now, I could leave you to it and you would do your best, right? Whatever you would do to integrate that. Let me show you what Wolfram alpha does, all right? Oh, it's just that right there. It's just a mess, right? That's not very pretty. Would you agree? So maybe we could get it, right? Maybe we could. Yeah? But integrals, as we saw, integrals are used to find, when we first talked about like what's the use of an integral, it was the area under a curve, wasn't it? And so what we would want to do is find the antiderivative and then plug in the endpoints and get a number, right? A numerical answer. And in the real world, numerical answers only have to be as precise as we actually need them to be. You know, if you're putting a lug nut on your tire, on your wheel, on your car, there's a certain torque, right? You know, whatever it is, 100 foot-pounds, you know what? 110 usually foot-pounds, right? That's what you need for the torque on a bolt. You could put 105 and probably be okay, right? But if you're torquing down a bolt on the engine mount for an airplane, you probably need to be dead on what the manufacturer says, right? There's a certain give and take, understand? And so with an integral, we just want to get a numerical answer. And sometimes we don't need it to be exactly dead on to the true answer. We just need to be close. And how close? Well, depends on if it's a lug nut or an aircraft bolt or a car bolt, right? So I don't know if this is making any sense. What we're going to do instead of looking at this function, which is very difficult to integrate, as you can tell, Wolfram alpha had some trouble with it, right? Well, it got it, but it's a lot of shit that we wouldn't want to spend time on, right? So maybe we just need to get close. So what we do is we rewrite this function as a power series. And remember, power series were just a bunch of powers of x, weren't they? And if you integrate a bunch of powers of x, it's very easy to integrate, right? If I give you x to the fourth, everyone could integrate that? 1/5 x to the fifth. So if I just have a bunch of powers, you could integrate that pretty easily. And then you would plug in your two limits of integration, get your numerical answer. And of course, you couldn't go all the way out in the series, could you? But how far would you go out? Well, as far as you needed to be close enough to whatever it is you're doing. So that's the focus of today. How do we approximate a function with a power series? We will answer this question in a little while. We're not ready for it, okay? We will get to this. There was another one I wanted to show you. I'll put it up on the board for my internet students. Arctangent of x over x dx. If you were asked to integrate that. So let's ask Wolfram alpha to do that. Arctan x over x. Looks pretty harmless, right? Oh, okay. It did spit out an answer. The answer looks pretty clean, right? Can you all see it? That's the answer. 1/2 I Li sub 2 of negative Ix minus Li sub 2 of Ix. What is that? Well, it says down there in the corner, Li sub n of x is the polylogarithm function. What the hell is a polylogarithm function? And those are imaginary numbers? Okay, so we're not even ever going to get that, ever, in this class. All right? So there are some things, moral of the story, that we cannot integrate easily, but we still want to be able to integrate. And so the power series is a tool that we use to get around these difficult integrals. All right, this was the difference between Leibniz and Newton, the two fathers of calculus. Newton had power series. Leibniz didn't have power series. He didn't get that far with the calculus. So there were certain integrals that Leibniz couldn't do that Newton could do. And I think for that, Newton is, to me, it's my opinion. I think Newton's version of calculus was a little more powerful. All right, so today we are going to be using extensively the geometric series, which I put up here. Just as a reminder, because I'll keep pointing to it, and just so it's on camera, we say that the absolute value of u, if that's less than 1, then the sum n equals 0 to infinity of u to the n, which is 1 plus u squared forever, should converge to 1 over 1 minus u. That's geometric series. Here we're using u instead of r, and a is 1. All right, we know this is true. Yes, you agree? All right. With that simple formula, we're going to do some crazy shit now, okay? All right, here we go. Let's start with this. This is gonna get, increasingly difficult as we move through the class. So what we want to do first in this example is express this as a power series. And I want us to also find capital R, which is the what? Radius of convergence, right? Not the interval of convergence. The interval of convergence is a little more involved, isn't it? Because what does the interval of convergence require that the radius of convergence does not require? That you check the endpoints, right? That's the difference between interval of convergence and radius of convergence. So this will be a little easier for us to do. So here it is. Here's the function. F of x equals 1 over x plus 5. Now, I think we would all agree, hopefully, that that's a pretty nice function. Like if I plug in 1, it's pretty easy, 1/6. Plug in 2. Like that function is well behaved. If I were to ask you to integrate that function, you could do that pretty easily too. It'd be a natural log or something like that, right? Not a difficult function, but we're starting simple, we'll build, all right? So can I express it as a power series? This is the only thing I've got right here. This is the only thing that I know, this thing right here. I know that this right here, anytime I see this expression, can be rewritten as this series, can't it? as this power series, as long as the u that I had, absolute value, is less than 1. So the question is, can I rewrite that to look like this? So let me show you. First, let me just change the order on the bottom. I'm going to put my variable on the right side because in this form, the variable u is over here, right? I have a 1 minus a u. I don't even, not even close, right? 5 plus x. What about this? Factor of 5 out of the bottom. Okay, so if I distribute this 5 back through to these two terms, I would get this back, wouldn't I? Yeah? And then I just peel the 1/5 out in front. So we good on this, on that so far? Yes, we're good. We got it, sir, no problem.
We're good.
We're good? Okay. Now, I need subtraction. I don't have subtraction. I have addition. So I'm going to add the opposite, like add a negative. So 1/5 times 1 over 1 minus, in parentheses, negative 1/5 x. That's a 5. We still good?
Yes.
Thank you. All right. Do you see now that we have 1 over 1 minus u? Yes? Now we have a 1/5 in front, but don't worry about that 1/5. The u for us is this, isn't it? That's the u. And so as long as the absolute value of this piece right here is less than 1, I can rewrite that with this power series, can't I? So that's what I'm going to do. So if the absolute value of negative 1/5 x is less than 1, then 1 over 5 plus x, which was the original function I was looking at, right, can be rewritten as a sum n equals 0 to infinity of what? Of what? U to the n. But what's u? Negative 1/5 x to the n. Do you agree? Understand that? Yes.
What about the 1 over 5?
1/5, yes, thank you. This 1/5, right here. Thank you for catching that. I forgot to put the 1/5 in front. Let me move this over. Okay. That better? All right, so this is a power series representation of this function. It is. But we want to make sure that we are comfortable converting it into what a general power series looks like. So remember what a general power series looks like. It's like sum n equals 0 to infinity, c sub n, x minus a to the n. That's a general form of a power series, isn't it? So what we try and do is we try and peel off the part that's the number that's going to keep changing. Possibly it might be the same the whole time. And then we want our x minus a constant to the n power. Right here, I don't have x minus a number to a power. I have negative 1/5 x, don't I? So what I'll do is I'll peel that apart first. So watch me do this. So this is equal to the 1/5 out here, okay? Sum n equals 0 to infinity. Now let me see how comfortable you are with this. Negative 1 to the n times 1/5 to the n times x to the n. So what did I do there? Peeled everything apart. That's right. I realized that that's the same as negative 1 times a fifth times x, right? All to the n power. And then just did the power on each one. Is that okay? Now, the reason why I peeled the 1/5 away from the -1 is because I have a 1/5 out here. Can I bring that 1/5 back in? What do you think? This is remember this right here is a bunch of things added together, right? The 1/5 would distribute to each one of those, wouldn't it? So it can actually be placed back into the series. So I'm going to put the 1/5 in here next. Let's see, sum n equals 0 to infinity, -1 to the n. What happens when I take 1/5 and I multiply it times 1/5 to the n? It's 1/5 to the n plus 1, isn't it? Now these are things, if you've been doing your homework, hopefully you've picked up on. 1/5 to the n times 1/5 to the first power. You add the two exponents, you get this, right? And then I still have out here what? X to the n. Right there. Now, do you see that this is more like the general form of power series? Do you see this part is your C sub n, and this part is your x minus a to the n? Y'all see it? That's the way the book's going to write it in the back when you're looking to check your answers. They're going to do this part. They're not going to stop here. They're going to go to this. Any questions? None?
When you distributed the 1/5 back in, that's assuming that you simplify it as much as you can, right? Before you put it back.
What do you mean?
That second line up there.
Here?
Yeah. When you said you're going to put the 1/5 back in,
Yep.
that's assuming that you simplified that as much as you can before you add.
I could have left it in here the whole time. I could have. Like, I could have put that 1/5 right there. But if I want to peel the x away from everything else, then I'm going to get the 1/5 eventually to come together. Saw another hand. No?
No, we got it.
Got it? Yes?
You said if -1/5 x absolute value is less than 1,
Mhm.
we can do that by just looking at that. Like 1/5 is obviously less than 1. But for something that's a little bit more involved, we would have to kind of do more to that portion instead of just
Well-
looking at it and saying, oh, that's.
No, I mean, we don't need to do any more to this in terms of like, this is the inequality we set up. There's nothing more to set up. But we do need to find the radius of convergence. And remember, the radius of convergence comes from this expression right there, right? So that's what I need to do over here.
So you're not done yet.
So I'm not done yet. This is the power series, okay, that represents that function. And now I want the radius of convergence. So for the radius of convergence, I come back to this inequality, and I split this up. The absolute value of -1/5 x is the same as the absolute value of -1/5 times the absolute value of x. That needs to be less than 1. What is the absolute value of -1/5? 1/5. And then what do? Multiply both sides by 5. So the absolute value of x has to be less than 5. So what's my radius of convergence? 5. So r is 5. Okay? Any questions? This is about as basic as it's ever going to get right here. Just for the sake of seeing it, what is this power series? Give me the first few terms of this power series. So like let's let n be 1 and then 2 and then 3, and let's just write out what we would get. And let's remember what we're saying too. We're saying if the absolute value of x is less than 5, then the function 1 over x plus 5, that was the original format, right? Should be equal to this series, right? So let n be 0, what do we get? -1 to the 0, 1/5, x to the 0, 1. So we get 1/5 plus, now let n be 1. What do we get? It's actually negative, so how about we make that a minus? And then n is 1, so what? 1/25 x. Now let n be 2. So what are we going to get? Plus 1 over 125 x squared. We'll go one more. What, minus 1 over 625 x to the third plus dot, 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 and that goes forever, right? You with me? All right, so let's try something. If I ask you right now, what's f of 0? Everyone would just plug 0 in here and get what? 1/5? What about that? Plug 0 into this. What do you get? 1/5, don't you? So they're the same, aren't they? At 0, they're the same function, aren't they? And as long, excuse me, been dealing with this all day. As long as the absolute value of x that you pick is less than 5, then these two functions are exactly the same. The difference is this one's easy to evaluate, right? Just plug in the number. This one you'd have to go out forever, which you can't do. What is f of 1? Well, according to this, it's 1/6, right? But according to this, it would be what? 1/5 minus 1/25 plus 1 over 125 minus 1 over 625 plus, and you'd have to keep going, wouldn't you? What we're saying is that this sum right here should add up to be what? 1/6. If you were to get on your calculator and start doing this, I promise you it's going to get closer and closer to 1/6. The further out you go, the closer to 1/6. Are you checking it? Well, you're trying to? Let me know if you get something close to 1/6.
Eventually, we're just having a series that adds up for each value of x that we plug into that series, and they'll eventually approach what we actually get.
That's right. Okay? But the bigger picture is this. If this function is easy to evaluate, or not evaluate, if this function is easy to integrate, you would never need this. But if this function is not easy to integrate, this would be easy to integrate, wouldn't it? Like, let's say we had no idea in the world how to integrate this function. How would you integrate this? Just term by term, right? What's the antiderivative of 1/5? 1/5 x. That's a 5. Okay, what's the antiderivative of this? Minus 1/50th x squared. Then plus here, what? 1 over 375 x cubed. Minus, and you keep going, right? So the value of that is if I'm trying to integrate 1 over 5 plus x, and let's say I'm trying to go from 0 to 1, and I have no idea how to integrate that, what I will do instead is just use the antiderivative. This is the antiderivative, right? 1 over x, or 1 over 5x minus 1/50th x squared plus 1 over 375 x cubed plus, and I'll evaluate 0 and 1. And if I plug in 1, it's pretty easy to see what happens. I mean, you could just see it's 1/5 minus 1/50th plus 1 over 375. If I plug in 0, it's what? 0? Right? If I plug in, well, no, because I've integrated it. So if I plug in 0, they're all 0, aren't they? Are y'all getting this or not? I mean, it's this right here, this integral. If it's hard to do, we could do the power series of it, integrate that power series, and evaluate that power series. And the closer I need to, the more significant digits you want, the further I'll go out into this series. As close as you possibly ever want me to get. All right, we're done with that problem. Any comments? Anything? What came first? Power, what do you mean, between what?
It's almost like you're saying break it up into different pieces to try to fix it.
Integration, yeah. But there were limitations. There were certain things we couldn't do. So let's get to this function right here. Now we saw that Wolfram had a problem integrating this function, didn't it? I mean, well, it got it, but it was a mess. So what if we wanted to integrate this function, which is, I'm not asking you to, right? I don't have an integral sign up here. I just want you to first convert that to its power series. Can you convert it to a power series? Well, you got to make it look like this first. 1 over 1 minus u. So can we do that? 1 over 1 minus what? Negative 7, x to the 7th. You don't need to factor out, like the last problem we pulled a 5 out, here you don't need to pull anything out. Because you already have a 1 here, don't you? We had a 5 in the previous problem, so we had to pull a 5 out. Everyone got that?
Sir,
Yes.
would it just be safe to say that you pulled out a negative from the x?
Yeah, if you want. Factored out a negative from x to the 7th, sure. Or you could also look at it as, you know, addition is subtraction of a negative. When you subtract a negative, it's the same as adding. Okay.
No.
No? Okay. So this is true, right? This is true? And if the absolute value of what's less than 1? Negative x to the 7th, right? That's the part that we are going to be calling our u, right? That's the u in the problem. If that thing, if the absolute value of it is less than 1, then we can rewrite this function as a power series. And the power series will be the sum n equals 0 to infinity of negative x to the 7th raised to the n. And be careful because the negative has to be in there, just like it was with the negative 5, negative 1/5 earlier. And then from here, I'll start peeling things off. So I'm going to take a negative 1 to the n, and then I'm going to do x to the what? So I'm looking at as negative 1 times x to the 7th, which was to the 7th to the n, and I'm looking at that as negative 1 to the n, and then x to the 7th to the n, right? So I can write this as x to the 7n, can't I? And just to get used to this, let's write out the first few terms of this series. So that's equal to, let's see, let n be 0, what do you get? 1. It's going to alternate. If n is 1, it's negative, right? And then x to the 7th. And then it's going to alternate plus. And now x to the 14th. And then minus x to the 21st. Are y'all seeing this? Go one more. X to the 28th, and then minus, oh, I lied, x to the 35th, and plus dot, 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 right? But this only works, right? You can only turn that function into this power series if what? This is true, right? If this isn't true, this doesn't work. So we have to be within the radius of convergence. And so let's look at that radius of convergence now. Because we've generated the power series, right? Here are the answers. This is our power series. Here's the power series written out, first few terms, right? And the radius of convergence, yes?
Could we just do the radius convergence first in order to figure out if we're wasting our time or not?
Sure. But the radius of convergence, I mean, you should have something. Like it's not going to be 0. Like no radius of convergence. You're going to have some radius of convergence. Do you know why? Yeah, because if I'm giving you a function, the only way it's going to have really a radius convergence of nothing is if that function is only defined at a single point. Does that make sense? So we're always going to have some radius of convergence. It might be an interval, it might be the whole number line.
Oh, okay, so it'll never not work?
If we're taking a function that we already have defined and converting it to its power series, we should have a radius of convergence. We should have something. Or else the function you're giving me to start with is a joke, kind of, right? Now, if I just give you a power series and I don't tell you where it came from, then you could have a radius of convergence of 0, which is the previous section. So I'm taking this, I'm peeling off a -1, absolute value -1 won't matter. So this becomes absolute value of x to the 7th less than 1. And then you can take the 7th power outside the absolute value. And then you take the 7th root of both sides. And what's the 7th root of 1? It's 1. So our radius of convergence is still, what? Well, what is it here? 1? So the radius of convergence is 1. So that means I've got to pick numbers between -1 and 1 for this to work. All right? Now you might be saying to yourself, well, that kind of sucks because, what was the original function? It was 1 over 1 plus x to the 7th. I'm telling you that you can approximate this with that power series as close as you want, as long as you promise me that the x's you plug in are between -1 and 1. So maybe you're like, well, wait a minute. What if I want x to be 2? Like, if I plug 2 into this, can we get a number? But if we plug 2 into this, it's not going to work. Why? Because 2 is outside the radius of convergence, right? So you're sitting there going, well, what's the use of it, right? Well, what we can do and what the next section deals with is that what we do is we shift the power series over. And we can move the power series closer to another number. And the way we would do it is just simply doing like a -2 in here or something, and that would move it over. That would move the whole function over. So there's a ways around it. All right. So now, if I ask you to integrate this, even though we can't do it algebraically, what we could do is we could say, all right, well, that's the same as integrating, what was it? 1 minus x to the 7th plus x to the 14th minus x, is this right? Plus,
28.
was it? Am I? Okay. Right? That's an infinite series sitting inside of an integral, right? Like that. Now, I can do this so long as what? As long as this is true, I can do that, right? And so now, integrate term by term. You get x minus 1/8 x to the 8th plus 1/15 x to the 15th minus 1/22 x to the 22nd plus 1/29 x to the 29th. You with me? 1/36 x to the 36th plus ... right? That's what that would be. Plus a what, though? Plus a constant. A lot of times we put the constant out at the front instead of the back because the back keeps going forever, right? So a lot of times books will put like c plus and then x and then the rest. I always throw it on the end, but okay? That would be the antiderivative, right? And so if you were asked now to integrate, let's say, between 0 and 1/2, could we do that? Yes, because 0 and 1/2, that interval, lies in here, doesn't it? So this would hold. So what I would first do is I would plug 1/2 into this, right? Compute it. And then I'd plug 0 into that, which would just be 0. And then whatever that answer is, that would be the numerical equivalent. Understand? Do you want to do it? I don't feel like doing it. You plug 1/2 into all these. So if I go back over to Wolfram Alpha now, and I ask it to integrate 1 over x to the 7th plus 1, and I say from 0 to 0.5, it should give me a numerical answer, shouldn't it? .499514. Well, guess what? If you plug in 0.5 right here, and 0.5 here to the eighth, and all that, and do all this on your calculator, you should be really, really close to .499514.
So what's the answer?
What do you mean? That's the answer, yeah. So what Wolfram Alpha did is exactly what I just did, what we just did. That's what Wolfram Alpha did. It converted the integral into a power series, it integrated the power series, and it evaluated the power series. That's how it got the answer. In fact, if you scroll down, a lot of times Wolfram Alpha will have a lot of other things in here. No, let me just type in, I'm not going to type in integrate. I'm just going to type in 1 over x to the 7th plus 1. And just watch, let's look at some of the things that come up. There it is. Oh, there's its graph, okay. There's always other stuff down here. Oh, whoa, whoa. What is that? Series expansion at x equals 0. Isn't that this right here? See this? See these two right here? Okay, so what Wolfram Alpha is doing is it's saying, okay, I'm giving you the first two terms of its series, power series. That OX13 means it went out as far as the 13th power of x and it stopped. The next one appears at what, 14? So you could actually have the computer go out. I mean, Wolfram Alpha is only going to give you that much. You probably have to pay to get the whole series if you want the whole series. You all understand? Now, I have a program. I told you the brains of Mathematica, or Wolfram Alpha, come from this program, Mathematica. And if I go in here and I just type in series and 1 over x to the 7th plus 1, and I want my variable to be x, and I'm not going to move it. Remember how I said you could shift it? I'm not going to shift it. Damn it. So I'm going to leave it at 0. 0. And how far do we want to go out? If I go 13, it's going to give me exactly what Wolfram Alpha gave me. See that? One. Yeah, I don't know why it says 14 here. But if I go, how far did we go? 30, 35? So what if I put 38? I should get the first, I should get all these that we just got, right? The ones that we just got right here? Okay. Makes sense? All right, next example. Same thing, we want to rewrite this with the power series. Let the fun begin. All right, now this is all we have to work with, right? And that looks nothing like this, does it? 1 over 1 minus u. So maybe you'll agree with me that this is equal to this. How did I do that? Partial fractions. Partial fractions. Remember how we split that apart? We did this when we were trying to integrate things. So I'm not showing this step, you know, where you have to find the A over this, B over this, and figure out what A and B are. Yeah? Yes?
Did you do this in your head?
I have this pre-done. Yeah, these These lectures are kind of have to be thought out a little bit before. Yeah, no, I had this all pre-done. Yeah, the stuff we're starting to get into now, it's hard to have it all up there. It's a lot of information. So, all right, yes, we good? Now, each one of these could possibly be written like that, right? This one, well, let me try and tweak it. How about this? How about, what can I do to this? I can rearrange it. If I rearrange it, it'll be this, won't it? And then on this one, I'm just going to leave it as 1 over, let me rearrange it, 1 plus 2x. So all I'm doing is rearranging so I can get my variable on the right side, on the bottom. And now, what can I do to this one? Pull a negative out, right? If I pull a negative out of the bottom here, can I slide that negative to the top? Negative 1 comes out, that negative can go on top? Yeah. Yes? So negative 1 on top, and on the bottom, 1 minus x. So I factored the negative 1 out. That negative 1 went to the top, went back through as a negative 1. And then on this one, I just need this to be a 1, which I have, and I need this to be minus. So I can rewrite it as, let's see, minus, and then 1 over 1 minus negative 2x. Y'all see it? It's just algebra. All I'm doing right now is just algebra, right? This part right here is like the u in that formula, isn't it? I'm going to call it u1 because I have another one over here. It's a different one, isn't it? This is a u, a different u. I'll call it u2. So I have two different series here, don't I? This is going to turn into a certain power series. This is going to turn into a power series. As long as what? The absolute value of that's less than 1 and the absolute value of that's less than 1. Both of them. Yeah, that's going to affect when we rewrite this as a series. All right, we good? All right, so here's where we are. If the absolute value of x is less than 1 and the absolute value of negative 2x is less than 1, then the original function will turn into this minus this, right? So on this one, I'm going to pull the negative 1 out. So that negative 1 is coming out, which leaves me with 1 over 1 minus x. What does 1 over 1 minus x turn into? Sum n equals 0 to infinity of x to the n, right? Everyone see that negative 1? I didn't want it there, so I just popped it out. Okay, over here, I'll have a minus sign, sum n equals 0 to infinity, and then what goes in there? Negative 2x to the n. Now you might think you're done, but you're not because this is two series, right? We want our answer to be a single power series. So one summation, not two summations. So let's try cleaning this up a little bit. Can I do this? Negative 1 bracket sum n equals 0 to infinity of x to the n plus sum n equals 0 to infinity of negative 2 to the n times x to the n. So what did I do here? What did I do? Actually, you know what? I want to do one more thing here. Sorry. Don't get mad. Negative 1 to the n, 2 to the n, x to the n. Is that all right? I decided to peel that negative 2 apart a little bit more. That's, yeah, what happened to it. So this has a negative in front, and this has a negative in front. So I pulled the negative out of both of them. And now if this negative were to distribute, it would go in front of this one, right? and then it would go in front of that one. That's why that turned into a plus. Yeah? No questions on that? We're still working here, all right? I need a single sum, so let me see if you follow this now. I'm going to leave that up there because I have to figure that out in a minute. This is equal to, let's say, -1 bracket. How about this? Sum n equals 0 to infinity of 1 plus -1 to the n, 2 to the n, x to the n. Whoa, what just happened? I went from 2 sums to 1 sum. Yeah, what do these 2 sums have in common? They both have this, right? So if I were to take, look at this expression right here. If I were to take this x to the n and distribute it through this parenthesis, wouldn't it go here to this 1, and then wouldn't it go to these guys right here? And so you'd have, what, x to the n? And over here you'd have all this junk x to the n inside of a sum, which means you can split it into 2 sums. So we're going backwards from this to this. That makes sense? All right, one more thing I'm going to do. I don't like that -1 sitting out there. I'm going to pass it back through. So what happens if I come through here with this -1? So this equals, no more bracket here because I'm passing a -1 through this sum. It changes this to a what? -1. And then this, be real careful here. If I multiply -1 times this, it'll be what? -1 to the what? n plus 1. And then I still have there 2 to the n, right? But all of that multiplied times x to the n. Do y'all follow that through, that negative going through? Everyone understand where this came from? That's here to here. Everyone understand where this came from? What happens when I multiply that times -1? What's -1 to the n times -1 to the first power? -1 to the n plus 1, right? That's where that comes from.
It doesn't affect the 2 at all?
No. And that was the thing I was going to ask you. Why doesn't -1 hit this? This all goes back to, basic algebra. Look, if I tell you 4 times 3 plus 2 times 5, I say distribute that 4 through. You'll do what? 4 times 3. And then are you going to do 4 times 2 and 4 times 5? No, you're just going to do 4 times 2. And if I throw an x on the end of this, are you going to pass that 4 all the way through to the x? No, it's just going to go through one of these. All right? It's either going to go here or just to the x. So you have to be careful with, algebra. Yes?
Why don't we just put a negative instead of a positive?
Where?
Where you distributed the negative sign? Yeah.
Why don't I do what?
Why don't you replace the positive? Yeah. with
You
the-
could have. Yes, you could have.
Can we do that?
You could have done that. There's going to be many different ways that your answer could look. The thing that won't change is that if we start to ask you to write out the first few terms, we should all have the same thing. All right? So let's do that. Let's write out the first few terms of this. Let's let n be 0. What do you get? All right, so this piece, this is our c sub n. This is our x minus a to the n, right? So let's see what happens. If n is 0, we get what? We have to do order of operations here. So this is n, 2 to the 0 is 1. -1 to the 1 is -1. So all this together would be what? -1, and then plus -1 is -2. And then x to the 0 would be 1. So the first term should be negative 2. Okay? Plus. Now let's let n be 1. So what happens if n is 1? This is negative 1 squared, so it's positive 1. 2 to the 1 is 2. So we're getting a 2 here. Minus 1 is going to be 1. But then x to the 1, x. Y'all are all looking at me like I'm doing some crazy stuff up here. Let n be 2. 2 plus 1 is 3. What's negative 1 cubed? Negative 1. Okay, I'm plugging in what now? 2. 2. Plugging in 2. 2 squared, 4. What was that? Negative 1. So negative 4, negative 5, x squared, and so on and so forth. Yeah? Now, I'm going to check it. What was the original function?
X plus 2 over 2x squared.
X plus 2 over
2x squared.
2x squared minus x minus 1. I'm not going to go out the first 38. I'm only going to go out the first 5. There it is. Did we get it? It looks promising, doesn't it? We got the first 3, right? So we should feel pretty good about that. So you're sitting there going, well, that can do it. Why are we doing this?
We have our degrees if
All right, what's my radius of convergence? I need to do some work on this one, don't I? This is the same as absolute value of 2 times absolute value of x less than 1. This is the same as 2 absolute value of x is less than 1, which means absolute value of x has to be less than 1/2. Agreed? The other one, absolute value of x is less than 1. So what's our radius of convergence? What do you think? 1/2? See, look, in order for that first series to converge, x had to be, the absolute value of x had to be less than 1. If you look at that graphically, here's 0, here's 1, here's negative 1. The first one, this one, said that we had to live in here for it to work, right? But the second one said we have to live in here for it to work. So we have to choose the smaller of the two intervals. Because if I say negative 1 to 1, I pick a number here, this one's okay, right? But this one's not. So you have to take the smaller of the two. So our radius of convergence would be 1/2. Good? All right. This is a theorem. This is what we call term by term differentiation and integration of series, of power series. Suppose f of x equals the sum n equals 0 to infinity c sub n x minus a to the n, with r being greater than 0. So what am I telling you there? Suppose we have a power series that has a radius of convergence that's greater than 0, which means that there is some interval, right, where this thing is going to make sense. Remember how we talked about the radius of convergence told us something like about the domain of the function? So we're talking about a function that can be represented as a power series and that it has some domain other than just 1 point, 0. So it's got some interval as a domain. All right? Suppose that's true. Then we have the following. 1. F is differentiable on A minus capital R, A plus capital R. So let me try and explain what this is saying. This A right here was the center point of our interval of convergence. If you look at a number line, A is right here. The radius of convergence being R means that we have some interval where this is A plus R and this is A minus R. Does that make sense? Here's the center of your power series interval of convergence. Here's that center plus R, here's that center minus R. So this theorem says that if this is a power series that has a radius convergence that's greater than 0, then it's differentiable. You can take the derivative. All right? Ron? What's up? Tired? Go run around. Do like 10 push-ups or something. All right, so it's differentiable. Well, if it's differentiable, I wonder what the derivative is. Don't you? No? What's the derivative? Well, let's write out what f is.
1.
Tell me what f of x is. Give me this power series written out, the first few terms. Tell me what it is. So let n be 0 and tell me what you get. C sub 0. So some number, right? And then x minus a to the 0, which is just 1. So is that okay if I just put c sub 0? Yes? Plus c sub 1, x minus a to the 1. Plus c sub 2, x minus a to the 2. Plus c sub 3, x minus a to the 3rd. I'll do one more. Plus c sub 4, x minus a to the 4th. Plus, keep going, right? So what's the derivative of this? If I say, all right, what's the derivative? What's the derivative of a constant? 0. Plus, all right, be careful here. This is a constant, so just bring it down. What's derivative of x minus a to the first power? What's derivative of x minus 5 to the first power? Oops, to the first power. What's the derivative of that? Derivative is just 1, isn't it? Just 1? Yeah? So bring the c1 down. Derivative of that is just 1. So c1 plus. Now here we have a little bit of a different situation. What's the derivative of, we're bringing the c2 down, right, as a constant. What's the derivative of x minus a squared? 2 comes down. Subtract 1 from the power. Take derivative of what's inside. So what should I have here? 2c2 x minus a to the first power and then times 1, which I don't need to put. What's the derivative of the next one? 3c3, c sub 3, x minus a to the second times 1 again. Last one. 4 c sub 4, x minus a to the third plus dot, dot, dot. Yes? That's what we would get? Now, I would like for you to tell me now, still working with this, I'm just out of room. I'd like for you to tell me what this series is in sigma notation. So in other words, right under this, I want you to tell me what the derivative of that is. So here's the original function. Here's what it was, right? We wrote it all out, and then we took the derivative, and here it is. I want you to write what that derivative is using a sum. Sum. Okay, so create this. Make this happen with the series. Let's look for a pattern. 2c sub 2, x minus a to the first. 3c sub 3, x minus a to the second. 4c sub 4, x minus a to the third. So isn't this always some number, c sub same number, x minus a to the number minus 1?
And T sub n?
So n c sub n should work, x minus a to the n minus 1? Okay, let me try that. N times c sub n times x minus a to the n minus 1. That's what you said? Will that work? Where does, if this is going to be our formula, which I agree, that formula is going to work, where does your n have to start? Ron? Where does n have to start? You gotta wake up, go outside something. Seriously, this is one of the most critical things when you take derivatives of the power series, what's about to happen right here. Just go walk around, Ron. Is he all right? You all right? Want some ibuprofen? I brought some today. Okay, can we start at n equals 0 like the original one was? Try it. If n is 0, you get what? 0, okay. 0, right? Yes? But we would get, what, this to the negative 1? Which would be division by it, wouldn't it? And that might cause a problem. Imagine that this is negative 1. That would be down the denominator, right? And then what if x is a in that problem? You get division by 0. So we do not want to start it at 0. Start it at what? 1. Will 1 work? So if I plug 1 in here, what do I get? 1, c sub 1, x minus a to the 0, which would be 1. So what would that all be if I plug 1 in? The whole thing, what would it be? 1, c sub 1, all that's 1. So wouldn't that just be c sub 1? That's this, yes? Then if you plug in 2, you're going to get what? 2 c sub 2, x minus a to the 2 minus 1 is 1. Then 3 c sub 3. So that should work, right? But the index is now what? Starting at 1. Please, Ron, do not forget this. All right? It goes from n equals 0 to n equals 1. Does anybody else see what just happened? Look at this formula for a second. Look at this. I'm just going to rearrange something for you. This is multiplication, right? Does anybody else see this? Look. What really happened? I'm going to erase all this crap right here. Try and summarize, if somebody tells you to take the derivative of a power series, how you would do it.
Take the n down.
Take the n down, just like you did with power rule, right? Take the n down, and then subtract 1 from the n. What do you do to this constant? Nothing. That's how you take derivative of power series. But there's one additional kicker. You've got to change the index and start at 1. Otherwise, it's incorrect. Understand? All right.
Why didn't we do that in the first place?
I wanted you to see where it came from. If I just came up here and said this is true, you would probably agree with me, but now hopefully you see why it's true. I could have just given you the formula and saved us 10 minutes, but I'm not real big on formulas if we can figure out where they're coming from. I think it's more important to know where it's coming from. So, all right, so that's part 1. Yes?
You always change the n, like forward 1? Like if it's 0?
If your original power series starts at 0, then this will go up 1. Yes.
Starts at 1.
If it's 1, it should go up to 2. But we're always going to try and get our series to start at 0 so that when we do this, it'll go to 1. All right, that was differentiation. What about integration? For integration, I'll just give you the formula, okay? You can go derive it yourself if you want. If you have a function and you want to integrate it, so you want to integrate a function, then you can integrate its power series. So keep in mind that all we're doing is replacing f of x with its power series representation, right? Everything in this bracket is f of x. And going off of what we just did, what do you think would happen? This would become a sum n equals, what do you think? Do you think it's going to we're going to have to start at 1 or not? It actually turns out that with integration, it does not switch, okay? But everything else goes as you would think. And what is that you would think? What do you think happens to this? Stays. Okay, that's true. And then what do you think happens to the power? N plus 1. But what do we always have to do when we did antiderivatives? We have to divide by 1 over n plus 1. So it's going to be the same thing. I'm going to have 1 over n plus 1 x minus a to the n plus 1. All right, do you see the power rule there?
Yeah.
But it's integration, so plus c. All right, so let's do an example here. I'm going to do one that we already did because this will keep it short. What if I want to integrate 1 over 1 plus x to the 7th dx? We just did this problem a second ago, didn't we? Yes? So let me do it a slightly different way. I want to integrate the sum as n equals 0 to infinity of negative x to the 7th to the n dx. So where did this come from? Look back in your notes that you're taking right now. What is this? This is the power series representation of 1 over 1 plus x to the 7th. If we switch that to minus negative x to the 7th, and then rewrite it. And then, of course, we had an interval of convergence. We had to make sure that the absolute value of x was less than 1. Go back and look at that, all right? But instead of actually writing it out and doing it one by one, let's try and use the formula that I just gave you. So first, we need to rewrite this as negative 1 to the n, and then x to the 7n dx. So what did I do there? What did I do here? I just take that negative right out, and that's because this is always going to be my what? What's that going to be in my formula? That's my c sub n. And this part right here is my x minus a to the n, except we have 7n instead of n, don't we? But we will use the same exact power rule that we just used. Let's see if you can do it. What do you think the antiderivative will be? So equals, no more integral sign. I'm about to take the antiderivative, right? No more integral sign. The antiderivative of this series should be itself, the same sum. I'm not changing the index. Do y'all see that? But no more integral sign. The c sub n should not change. And then, I'm supposed to do like 1 over n plus 1, x to the n plus 1. But n for us here is really what? 7n. So this should be 1 over 7n plus 1, x to the 7n plus 1. And then plus some constant out here, right? Plus some constant. Anyone have any issues with that? Everyone see what I did? I wonder if we can figure out what that constant is. Maybe. We'll deal with that in a minute. There was something else I want. Oh, can we check this to see if it works? If this gives us the right answer? Let n be 0, and what do you get? And I'm going to write out a first few of these. 0 here, we get what? 1, 1, 1. So just x to the 1. So what is it? You said 0. You said 1. Sorry. Negative 1 to the 0 is 1, 1, and then x to the 1. So just x. And then what's the next one going to be? Minus 1/8 x to the 8th, and then the next one will be plus 1. You're plugging in 2 now. 15th x to the 15th minus. Go back and look in your notes. Is that what we got when we integrated a little while ago? When we integrated it, that's what we had? Do you see we could have got the same thing using that formula instead? We only have 30 minutes. We haven't even... Okay. Y'all still hanging in there? Next example. I want us to rewrite this. I want us to rewrite this using a power series. Okay, a little time stamp here on my video. Okay, this is my little time stamp. Things are going to get a little strange right now, okay? Right? Things are about to get a little weird. Because this is what we need, okay? This is what we need. Yeah, the other one we did partial fractions, we were able to get this, weren't we? There's nothing you can do by just looking at that algebraically to rip it apart, can you? But you're recognizing something here. The derivative of that is something that's close to that, isn't it? Yes? So pay close attention here. The derivative of that is what? The derivative of f, I'm just thinking out loud here. Derivative of that is what? 1 over 1 plus x. That's what I'm thinking, right? That's a derivative. That means the antiderivative of this is that. Right? If the derivative of that is this, the antiderivative of that is this. So could I write this? That this is the antiderivative of that. You can't get it backwards. You can't tell me that this is equal to the derivative of this. Right? Understand the order of this? If I tell you to find the antiderivative of that, everyone's going to say, oh, the antiderivative of that is that, right? Plus c. But 1 over 1 plus x can be written as 1 over what? 1 minus negative x? Can't it? And 1 over 1 minus negative x can be rewritten as a power series. What power series can it be rewritten as? Integral still. Sum n equals 0 to infinity of negative x to the n dx. Backtrack. Rewrite that as a power series. I have no friggin' idea. But The antiderivative of this is this. But that is this, and this is a power series, and I know how to integrate power series with a formula. But I have to make this look like c sub n x minus a to the n. So I need to work with this still a little bit, don't I? What do I have to do? Peel out that -1, right? So that is equal to integral sum n equals 0 to infinity, -1 to the n, and then x to the n dx. Am I free to use the formula now? Yes? Use the formula, right? So am I going to write the integral sign again now? No, because I'm about to integrate. So I'm integrating a series, which means it's going to start at n equals. Are we integrating or differentiating? We're integrating, so you start at 0 still. To infinity. -1 to the n. Do I do anything with this? No, that's your c sub n. So nothing happens to that. But the x to the n is going to become 1 over n plus 1 x to the n plus 1. Plus c. You got it?
Yes.
Does everyone understand that this series does not represent the antiderivative of that? This series represents that function. This is that, all right, within the radius of convergence. The way we got it was to use some information about the fact that the derivative of that was something we knew. So we didn't just integrate that, we just found what that was using a tricky backdoor in, if that makes sense. Now, this is correct. There's nothing wrong with that. But we need to get comfortable doing something because of where we're going with this. We always like our power series when we write them to be to the n power, don't we? X to the n. I mean, that's what a general power series always looked like, right? It was c sub n x minus a to the n, right? That's like the most general form. And it was sum n equals 0 to infinity. That's what a general power series looked like. And I think you asked me one time, does it have to be 1? Did you say that? Someone said that. Does this have to be 1 for a power series? Or maybe, I don't know who asked. But for a power series, this does not have to be 1 for it to still be a power series. All right? Or sorry, it doesn't have to be 0. It can start at 1 or 2 or 3. All right? But this we like. The thing with x in it to the n power. Right now, the thing that has x to it has n plus 1. Right? I'm about to make it be x to the n instead of x to the n plus 1. And what I'm going to do is what we call a shifting of the index. You ready? I want, right now, I'm going to shift my index. Shift index. When we say index, what I'm referring to is this index right here. This is our index. N equals 0 is the index where it starts to infinity. I'm going to shift it. My goal is to make this exponent be an n instead of an n plus 1. What would I have to replace n with to make that be an n, just an n, if I put it together? N minus 1. Does everyone agree if I replace that n with n minus 1, this will turn into n up here? So what I'm going to do right now is everywhere I see an n, I'm going to switch it to an n minus 1 and watch what happens. You ready? I'm going to rewrite the whole thing. Everywhere I see n becomes n minus 1. Sum. N minus 1 equals 0 to infinity. So that looks a little weird. We'll get to that in a second. -1 to the n minus 1. 1 over what? What's n minus 1 plus 1? N. X to the, what's n minus 1 plus 1? N. You see what I've done? Plus c. Now I need to resolve the index, correct. So what is this equivalent to? N is 1. Right, if I just add 1 to both sides of this, I get N is 1. So this becomes N equals 1. So if you take this power series, starting at 0, this is what it looks like, right? But if you shift the index, so change the index over to starting at 1 to infinity, it has the effect of converting x to the n plus 1 over to x to the n. And that is a skill you need to know how to do. No questions?
Is that why the derivative shifts to n equals 1?
The derivative switching to n equals 1 has to do with the fact that when you take the derivative of that first piece, the derivative is 0. Like if you write a power series, that first constant is 0. So when you try and regenerate that series, you don't want that piece there. So you move it by 1.
You did this in one of the homework videos as well.
Pardon?
You did this in one of the homework videos?
I did. I shifted. 8.5? Did I? Okay, good.
We were just talking other conversion steps.
Okay, good.
That's this one, right? 8.5.
I don't remember him doing that. I watched the
8.4.
Oh, okay, well, I haven't gone through it before yet.
All right. I think this is the last one we're going to have time for. Same instructions. I want us to rewrite this as a power series. Well, that'd be too easy, right? Yes.
Are we going to have trig functions in these?
You could. That's where I'm headed. Yes, we're headed there. Inverse trig functions. Anything, basically. But there's not enough time in this class. Just not enough time. We actually need like another 3 classes to get through this properly. I think. We need like another week.
Does it
But-
matter that we're not going to complete everything we're supposed
I think you've seen enough right now that you'll be okay. Yeah. All right, let's do this. If that were 1 minus x and that were it, we'd be okay, right? In the last problem, we saw natural log. What do we have? Natural log of 1 plus x, and we realized, hey, the derivative of that is something I know, right? This is the opposite. It's not the derivative of this that you know, it's the antiderivative of this that you know. So let me just, on the side, thinking out loud, what if I integrate 1 over 1 minus x to the second power? What if I did that real quick? Basic u substitution, maybe? U would be 1 minus x. Du would be negative dx. So you're off by a constant, aren't you? So rewriting this integral would become integral negative 1 over u squared du, which is the same as negative u to the negative 2 du. And what's the antiderivative of that? Power rule. So is it u to the negative 1? Because negative would come out, subtract 1. So that's just 1 over u, isn't it? But what's u? Minus x. So this is 1 over 1 minus x. All right. So let me recap. You're looking at this and you're like, man, this is all I know, right? It's all I'm ever comfortable with. Then we realize, wait a minute, hold on. That's the derivative of this. Why? Because the integral of this is this, right? So if I differentiate this, what should I get? That, right? differentiate this, I get that. I'll say it one more time. If I differentiate this, if I take the derivative, now I'm using what's called Leibniz notation, that's just telling everyone I'm about to take the derivative, treating x as my variable. If I take the derivative of this, that's equal to what? This. So I'm continuing this. This is equal to this, which is equal to the derivative of this. So this is all one string of equals. Yes? We all agree? But this I can rewrite as a power series.
It's kind of already there.
It's already there. Isn't that beautiful? So this derivative of this power series, n equals 0 to infinity of, this is a pretty clean one, right? X to the n. And how do you take the derivative of a power series? So I'm ready to take derivative. No more derivative symbol. What? N is 1. Why? Because that's what we said happens when you take derivative of a power series. That index shifts up 1. N is 1, but then for this, what? N comes out front, x to the n minus 1. Done. Within the radius of convergence, which I'm not even looking at the radius of convergence. Now, what if I asked you right now to make this power series have x to the n instead of x to the n minus 1? If I asked you to shift the index to make that x to the n, what would you do? You'd replace all n's with what? N plus 1s. And I'd like for you to do that. Let's replace all n's with n plus 1s. So sum n plus 1 equals 1 to infinity. I'm replacing this n with n plus 1. I'm replacing this n with n plus 1, which becomes x to the n, right? N plus 1 minus 1. And then the last thing is, what's this? N is 0. So you get that this is equal to, I'm just put it up here, this is equal to the sum n equals 0 to infinity of n plus 1 x times x to the n, as long as you're within the radius of convergence. Looks like I have time for more. I have time for one more. That only took us 5 minutes. All right. Here we go. You ready? We might go a little over on time. I hope everyone doesn't have anything planned after this class. I'd like to change that. Let's change this to x over 1 minus x, the entire quantity cubed. There's the original problem. Rewrite it as a power series. So first thing I'll do is this. Right? Okay. Do you see anything? You like this, right? You like the 1 minus x on the bottom, but the cubed is no good, and the x cubed on top is no good, right? Can't cube root. No, can't cube root. It's not. You're not gonna be able to cube root a series. So, how about this? Just follow me on this. That's what I need mostly from you right now, is just to follow everything I'm doing. Do you agree with that? Okay. Now, wait a minute. This. I think that's the derivative of something. Don't you? So let's try it real quick, thinking out loud. What if I integrated that? Isn't this the same problem we just did, except a cubed instead of a squared? So this would turn into integral negative 1 over u cubed, wouldn't it? du, if I do the same substitution as earlier, which is integral negative u to the negative 3 du, which would be what?
One minus x.
What is it? 1/2 u to the negative 2. Let's just check it. Negative 2 comes out, hits this, becomes negative 1. That's this. Subtract 1 from the power, you get negative 3. So do you agree that's the antiderivative? What was u? 1 over, or I'll write it this way. Write it this way. 1 over 2, 1 minus x squared. Yes? All right. All right, so I have to think through this again. This is this the derivative, or no, I'm trying to trick you. Is this the antiderivative of this? Am I tricking you? No, this is the antiderivative of that, right? Which means that that is the derivative of this almost, isn't it? Look, if I take the derivative of this, I should get that, shouldn't I? But there's this 2 here, this 1/2. Do you see that? So we have to somehow account for this. I need someone to help me in what I'm going to write on the next line. X cubed times. You just said that this is the derivative of what? This is the derivative of that down there? So I'm going to write this is the derivative of everything I see down here, right? 1 over 2, 1 minus x quantity squared. Now, are we okay with this? You sure? Sure? No issues with that? Okay. Now, I'm still continuing my equal sign. That is equal to, leaving that x cubed out here, actually, see that 2 on the bottom? Since it's a derivative, constants can come out, can't they? So how about if I do this? 1/2 x cubed times the derivative with respect to x of 1 over 1 minus x, that quantity squared. Yeah? Now we're hoping to turn this into a power series, aren't we? Yes? You understand what's about to happen? What is this? The previous problem. So we know what it took to turn that into a power series, didn't we? We did that in the, was it the previous problem? 2 previous problems, right? Or was it the previous? No, it was the previous problem. But from the previous problem, we already did the work, didn't we? We don't have to go back and redo this. What was this written as a power series? You should have it written down right there. Do you have it written? Who has it written? Anyone?
Summation n
Let me
equals 0.
Let's see. Yes, and let's do the 0 one. Okay. So that was, and notice I'm still keeping the derivative, but this right here is the power series n equals 0 to infinity of n plus 1 times x to the n from previous problem. Right? So we know that our original function is this times the derivative of that, but that is this power series, and that we can take the derivative of. because this is x to the n, right? So we can do the power series now, the derivative. So 1/2 x cubed times, what is the derivative of this power series? So sum, n equals 1 to infinity. Do we do anything with this? No. But we do n down, x to the n minus 1. Nope. Nope, we're still not there yet. What I'd like to do now is take care of this x out here. This is x cubed, right? So since this sum involves n and not x, right? The thing that keeps changing is the n. The x is not affected by the n. This one, this is, right? This x to the n. I can pass this 1/2 x cubed into the sum, multiply it in. And when I multiply it in, I should get this. Sum n equals 1 to infinity of, let's see, the 1/2. I'll sit that in front of the n times n plus 1, which is these two just written backwards, and I put the 1/2 in front of them. And then I have x to the n minus 1 times x to the third power. And can you put those two together? Add the exponents. X to the n plus 2. So equals sum n equals 1 to infinity, 1/2 n plus 1, x to the n plus 2. That's your power series. But I'd like to have it as n power, not n plus 2. Can you give that to me as an n power instead of n plus 2 up here? You're going to have to replace all your n's with n what? Minus 2. So let's go replace all our n's with n minus 2's. Right here. Sum, if this becomes n minus 2, and I add 2, what do we get? 3 to infinity, 1/2. This n becomes what? N minus 2. This n becomes, or this n plus 1 becomes n minus 1. And then this becomes x to the n power. Still have time. That is the power series representation of that function.
Okay, so essentially what we want to try and do when we're solving these problems is try to find if we can integrate or differentiate part of it.
Yeah. Yeah. Let me show you the next example. I'm not going to do it, but let me show you the next problem that we are going to do next class. And this will be we're going to do this one. F of x equals x cubed minus 2x over 1 minus x, that quantity cubed. I don't know. Maybe we could do it right now. I don't know. I know it's almost time, right? I got 3 minutes. Just tell me if I can do this. Can I do that? Okay. Do you recognize the first part? What is that first one over there? That's a previous problem, isn't it? What did we get after all that work? What did we say that this series was? Sum n equals 3 to infinity, 1/2 n minus 1, times n x to the n. Wait, what was this one? N minus 2, n minus 1, right? N minus 2, n minus 1, x to the n. Yeah? This one, on the other hand, is a little more work, because what we'll have to do is look at that one as negative 2x times 1 over 1 minus x cubed. Now, this right here, didn't we do that a minute ago? Yes? Can anyone tell me what that one was?
1 over 2.
So this is minus 2x, and it was sum? I want it as a series. What was this piece written as a power series? Let me see.
You gotta pull out 1/2
Yeah.
from this.
It was this one right here.
And then you see what I mean, like
Yeah.
that 1/2.
Okay, so this should turn out to be 1/2 on the outside, power series, n equals what?
Or, yeah, n equals 0 to infinity, n plus 1 times x to the n.
N plus 1? Was it?
Oh, dx.
Yeah, we need, hold on. Who else? You're confused? Anyone else? Everyone else is confused? Do you have it? Let me see it. Yeah, that's the one. That's the one. Okay. So you got to go back and look in your notes. It's this, and it's n was 1, right? And then it was n plus 1 times n, x to the n minus 1. Is that what you have? Yes? Sure? Double check. Exactly? That's it? Yes? This is this. And then the 1/2 came out. And then this and this go away. I'm out of time. I can see you all running for the doors. If you got to go, you got to go. But I've come too far now. Can't turn back now. Okay, this, I still have an x out here. What will happen if I push that x into here? This will become together x to the what? N power. So we have that. Pardon me?
We don't need to choose the limit, the bound.
We're about to find out. There is a problem, though. We do have an issue that we need to deal with. You see that, though? They both are x to the n's? Double checking. X to the n. Yeah, this looks right. Okay. What's the problem? Anyone see what the problem is? They both have x to the n's. These c sub n's don't really matter. What's the problem? One of them starts at 3. The other one starts at 1. So you might be thinking to yourself, all right, let me just make these both start at 1. Or let's make these both start at 3. The problem is that if I try and tweak this to make it a 3, I'm going to change this. This x to the n is going to change. And I want these to be the same. Sorry?
Wasn't that n minus 1?
It was, but I brought that x in from the outside. There was an x on the outside I brought in. If you got to go, you got to go. Here's what I'm going to do. This right here minus. Let's let n be 1. If n is 1, what would I get? 2x. Right, if n is 1? What if n is 2? So plus, let n be 2. 6x squared? Yeah or no? Okay, then I can say n is 3, and then n is 4, and then n is 5. What if instead I say plus now the sum going from n equals 3 to infinity of n plus 1 times n x to the n? So what I essentially did was peeled off the first two of these. I peeled them off. Now this sum goes from 3 to infinity. You see it? And so when I put this out front and distribute my minus sign through, then, yeah, well, I'll finish it. You get the gist of it. Now you could start to put it together.